talking about was the Gaussian model, and what to do with the denormalization group.
স্যার বোর্ডটা একটু জুম করা যাবে? বেশি হ্যাঁ, এরপর একটু ফোকাস করতে হবে স্যার। হ্যাঁ ঠিক আছে ঠিক আছে।
So what we were talking about is the Gaussian model, where the free energy is given by F, which is integration over all space m square by 2 phi square plus half grad phi whole square. This in momentum space ddp over 2 pi to the power d m square plus p square by 2 phi p phi minus p. And the idea was that what you it's a question of implementing the renormalization group. So what I have to calculate is the partition function, the functional integral over this minus integral ddp over 2 pi to the power d. So m square plus p square over 2 phi p phi minus p, which you now split as in d phi e to the power. So I'm going to write this as ddp over 2 pi to the power d. This is p less than, so I'm going to remove the momenta in the range lambda over b less than p less than lambda. So the integrals in momentum space go up to a cutoff lambda, which is arbitrarily high. And I split this into 0 to lambda over b m square plus p square over 2 phi p phi minus p minus integral ddp greater 2 pi over d lambda over b to lambda m square plus p square by 2 phi p phi minus p. So the point was that we can do this integral, a series of Gaussian integrals which we get out of that. So it's some pi p equal to lambda over b up to this, and p square plus m square to the power half, and some numerical factors over here. And what is left is d phi, which are the lower momentum, this d phi less e to the power minus integral, this goes from 0 to lambda over p m square plus p square by 2 phi p phi minus p. So that's so this is the part that is left. And now the point is, you want to, so this was step 1. Step 1, integrate out momenta between lambda greater than p greater than lambda over b. This is the equivalent of in real space where when we did integrate over a set of spins to increase lattice spacing. So that step which we did when we did the Ising model, that you first integrate over a set of spins and you increase the lattice spacing. Over here, we have it is in momentum space, and I have integrated over a set of phi's. Which phi's? Now, those phi's which have a moment, which correspond to a momentum which is high, I've removed them. And so now I have a situation where I need to essentially do this repeatedly. That is what one did over here. One had this lattice spacing, which you could go on increasing till you went up to essentially an infinite number of times. So, all right, now I have this over here, but I have to do this process once again and again. So what I need to essentially rescale back. So scale the momenta to bring cutoff back to lambda. I have to compare the m with the m that I started, out with over here. This Hamiltonian or free energy has to be compared to the new. So if I want to do the comparison, the new has to look exactly like the old, with only the m changed. It is then that I can say that, look, everything else remaining the same, the m has now become some m prime. So that is the thing which one needs to do. And therefore, the next step is that you scale the p goes to some q, which is q divided by b, so that this step over here, the z becomes equal to, you now have whatever these constants were over here, and then d phi less, and it is e to the power minus integral back to lambda, and it is ddq by b to the power d, and I have m square, and it is q square over b square, and it is phi minus q. So that's where, and now the point is, what I need to have is that q should look the coefficient, in order that I can compare the m's, the coefficient of this p square has to become exactly the same. So the q is now changed, the q square over b square has to become some momentum q square, and it is 2 plus d, so it is q square over b to the power d plus 2, and that has to go to some momentum p prime square, so that it becomes d phi less e to the power up to this, and then it is dd some p prime, and now it is m square. So over here, the fact that q is b square, you have left b square over here, and now it is plus p prime square, and it is phi p prime, phi minus p prime, which is equal to d phi less e to the power minus, and then it is d dp prime square m prime square plus p prime square phi minus p prime phi p prime. So after this sequence of steps, there is some sitting over here. After this sequence of steps, what I had over here is back in this form over here. So this integrating, rescaling, so removing this out, integrating these, removing these degrees of freedom, and then rescaling to bring it back exactly to the same form as before, rescaling the fields to bring it back to the same form. It now, what we see, we have the same form of the Hamiltonian, the free energy, except that it is, the process has changed m square to m prime square, which is equal to m square b square. So that is what the Gaussian model is all about, and that is the procedure which one does for this renormalization group procedure in momentum space, removing a set of degrees of freedom and seeing how the parameters of the problem change. There was just one parameter over here, which is this m square, and what if to recall what m square is some constant times t minus tc. That's what the meaning of m square is, that m square is equal to a0 into t minus tc. So it is t minus tc ইনফিনিটলি মানে যে ল্যামডা নিয়ে শুরু করেছিলাম সেই ল্যামডায় ফিরে গেছি। হ্যাঁ 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 হ্যাঁ, মানে it is as close to infinity as possible. So this, which was our starting point, has now, after this rescaling procedure, gone to ddq over or ddp prime, as we wrote, by d m prime square plus p prime square by 2 phi p prime phi minus p prime m prime square is equal to b square m square. So that is what we have done. So all right, now question is, how do I take the next step over here? So the next step comes to saying, going back, that I have to relate this thing to what I want to calculate. What I want to calculate primarily are critical exponents. Critical exponents is what we are after. And so what we need to know, and the big thing about the critical point is that there's a correlation length which goes to infinity at t equal to Tc, and the behavior is psi proportional to t minus Tc to the power nu when t has become very close to Tc. So that is that is one of the critical exponents which is very important, and this critical exponent gets related to the other exponents like susceptibility, to which it is related by 2 minus eta times nu. Eta is anomalous dimension index which is very nearly equal to 0, and then that gives you gamma. Then there is, you get, so all right, then there is the specific heat. This is the susceptibility. Susceptibility here is the alpha, which is the specific heat index. And so alpha is something, it is nu, it is the correlation length which has the exponent nu, which is what we will be calculating. And therefore, the thermodynamic quantities like the susceptibility and the specific heat get related to nu through gamma equal to 2 minus eta times nu, and alpha has to get related as well. So what we now want to do is look at how does alpha get related to this nu over here before we go ahead and find the nu for this Gaussian model. So we have done it actually. I mean, the Gaussian model was worked out where by just doing the integral. So if you, at every point, I would strongly advise to go back. I mean, there it was all very simple. We simply did the it's a quadratic quantity. We did the calculation, got the free partition function, and then got the actual thermodynamic free energy out of it, and had calculated all the exponents. We are doing it through the renormalization group once again, so that you know that the procedure which is the of renorm actually gives you the correct exponents. And the advantage of this would be that I can now add on, I would be able to add on the quartic term, make it from the Gaussian to the Ginzburg-Landau, and then use the same sort of procedure to calculate the correction to the Gaussian exponents. So that is why the Gaussian, the phenomenology of doing the Gaussian should be absolutely clear, so that the complexity of the next step is just algebraic complexity and nothing else. So we come over here, and now I need to relate the nu to the alpha. The nu will be obviously obtainable from here easily. It is the, once I know the nu, I can get gamma. How do I get the alpha? So we go back to the physical quantity, which is the free energy. This is really the, over here, it is the, there is a, this is the free energy functional, and this F over here is actually the thermodynamic free energy. So the thermodynamic free energy it has the critical point behavior, which is F to the specific heat has the behavior which is T minus alpha. The specific heat is T times 2 del to F del T squared. This T does not have any criticality. All the critical behavior is in this F over here. So if C goes as T to the power minus alpha, this free energy over here has to go as 2 minus alpha, so that two derivatives over here brings up the C. So the free energy in terms of T, which is how far you are from the critical point. So T is the reduced temperature, which is T minus Tc over Tc, and that's that. So, all right, now comes the question of F. This F is an extensive quantity. So extensive quantities have they are proportional to the volume. Volumes change under the rescaling transformation, and therefore one needs to, if I'm going to pick up the thermodynamic alpha from over here, it is not the more convenient quantity to use is the free energy per unit volume, where the extensive part is taken out and it is just the free energy per unit volume over here, so which has the behavior really, which is 2 minus alpha. So it is the intensive part of this thermodynamic free energy. When we say that it goes like T to the power 2 minus alpha, it is just the intensive part of it, which means that it is really F over V, which is it's the intensive free energy, which goes as T to the power 2 minus alpha. So it is F which goes as this. And now the point is that F is equal to, so if I do a rescaling transformation, then the F which has a question is, how does F behave under rescaling? It becomes F prime, which is the free energy is a number. F is equal to minus kT log Z. So F is just a number. I mean, it does not have the scaling, any obvious scaling as you change the length dimension. It is simply minus kT log Z, and it is F prime, which is the one which is going to have if I scale distances by a factor, by a scale factor, so that V is, you use a scale factor of B, so that V becomes your scale increases by a factor B, then the distances measured in the new scale is the measure in the new units is down by a factor of B. So this is F prime is equal to V prime, and V prime itself is in numbers, in actual measure number, so many units is V over B to the power D. So F prime is equal to F divided by V to the power B times D, which is equal to F to the power B by D. So if I do a rescaling transformation, then the free energy per unit volume, so this is equal to the previous free energy times B to the power D, where B is the scale that I have made use of. So this free energy, which we started out with, so let's say that the free energy that I start out with is at a temperature T. So free energy at a temperature T, which is at which corresponds to a correlation length which is xi. So F of T, which is at some temperature T where the correlation length is given by xi. And then the point is that, look, at the next step, this f of t, which I started out with, is going to become, so this some f of t prime. Question is, what should be the, over here, you find that this f is equal to b to the power d. So the what one is after is what is the transformation, as the correlation length changes, where are we, how does the f, this, what is the dependence of f of t on xi, which is proportional to t to the power. So that is what one is after. So what is the dependence of this free energy per unit volume in terms of this? I know that the free energy per unit volume has the behavior in terms of T, which is 2 minus alpha. Can I write this in terms of, so it's a question of being able to write it in terms of the f over here in terms of the correlation length, and then relate the correlation exponent to this exponent over here. So that's the game that we are in the business of playing. So here we are. This is the free energy that we start out with. So F is the step 1, and then the next step is this. So if F is at temperature T, this is at, let me write it in terms of how far away you are from criticality. So if you are T, which is delta T, so T, make it clear, there it is, f of T, and I have gone to the next step, which is change, f of T is over here. This is equal to f prime. So it is f prime times b to the power minus d. F prime over here is essentially, where has T gone? The transformation takes me, this transformation takes the T and takes you to some lambda times T prime. So there is so this is what we learned over here, that here is m square of the model is proportional to T, and the point with the renormalization group is that what has happened is that this has scaled, this T minus Tc has now changed by a certain scale factor. Let's call it some lambda, which is as you which is b square over there. So the new T square, which is m prime square, so it is this is equal to m square times b square. So let me put the lambda with the others on the other side, and it is the T prime, which is equal to lambda times T. So T prime, which is equal to lambda times the T over here, that is the transformation that is taking place. So here is xi dependence on this. So f of T is equal to f prime at, so this is f of m at this is when the temperature is T, and now it is temperature is lambda is this is equal to and your f prime over here, which is at a different temperature, which is T prime. So this is f at T prime, which is at lambda T. And so this is, let me put in the in between steps. F of T is f at T prime, and then is equal to b to the power minus d. That is what this step is telling you over here. And then it is f of T prime is related to f of T by f of lambda T, which is equal to b. And then you go one more step, and it is f lambda squared T, and then it is b to the power minus 2d, and so on. So f of T goes as this over here, and then it is equal to, so you go n steps, f of lambda n to the power T, which is b to the power minus n times d. So f of T is what you started with. Next step, you have f of T prime. It is changed by a factor of b to the power minus d. Then if you go another step, you pick up, so this is just writing T prime, and then you go another step, the lambda, because pick up another factor of lambda, and the n factors of lambda, and you have an n over here. So what you do is that every time you are moving away and away, more and more away from the critical point. So this transformation over here is essentially moving you away from criticality, and eventually you choose a lambda, choose n large enough so that T times lambda n is of the order 1. So T times lambda n is equal to unity. So this is equal to, that tells you that lambda it's this, so all right, it is b to the power minus, what I'm interested in is b to the power minus nd. That is the thing which is of interest. It is, this tells me that n log lambda is log of 1 over t. So n is equal to this. So b to the power minus nd is equal to, so your n is the quantity n, as you can see from here, is this is b to the power minus d, and n is log of 1 over t by log of lambda. So b to the power minus nd is b to the power minus d log of 1 over t over log lambda, which is equal to, so this is equal to 1 over t so this is an 1 over, let me write this as d log, this is d log of 1 over t to the power d log of lambda, and so if I write it in that form over here, it is this d which I had over here shifted to 1 over d. So it is b to the power minus log of 1 over t to the power d log lambda. And then you want to write this as 1 over t to the, so all right. So b to the power minus log of 1 t to the power minus d divided by log of lambda over here, which if I take a log of this quantity is log b is minus log B log T to the power minus D log of lambda. So if I take this D, so I'm looking at the quantity B to the power minus, and I'm taking a log of this. So I'm taking a log of this whole stuff over here, and that is minus log of T, which is D log B log of T divided by log lambda, and therefore this is equal to log of T to the power, this is log of T to the power, this whole quantity over here, which is D log B divided by log of lambda. So here we are. This is after I have gone n steps as such that T lambda n is equal to this, I have B to the power minus ND become B to the power n is substituted by that. So at the end of the day, B to the power, where was I anyway? It was log of it is B to the power minus n log this. So it is B to the power, where am I? It's a log of this, after this quantity over here, and B to the power, what has happened? Is yeah, all right. So it is this quantity which I'm after, B to the power minus D log T. So B to the power, I'm after B to the power, this quantity over here, this is just a second, let me get this right, or else this is going to be a mess. So it is B and it is T to the, so it is D log T divided by log lambda, right? So log of then D over here makes it T to the power D, and a minus sign makes it 1 over T to the power D. So B to the power minus ND is equal to B to the power minus that, and at the end of the day I have this f of t equal to something which is of order unity, a number of order unity, B to the power minus ND, which is this number of order unity, and then it is B to the power, that's what I have, B to the power D log T divided by log lambda, which is order 1 quantity, and then it is a T to the power, so it is B T to the power D log B divided by log lambda, right? So B to the power D log T by log lambda, take a log, it is log B into this, and over here take a log, it is log T into this. So order 1, so f of t is T to the power D log B divided by this. So that is what the free energy is doing to it. So that is what the free energy is doing. The free energy per unit volume has the temperature dependence. So this f of t is proportional to T to the power D log B divided by log lambda. So but f of t, that is 2 minus alpha. So 2 minus alpha. So 2 minus alpha is equal to d log b divided by log lambda. So that's one identity that we have obtained, that 2 minus alpha is d log b divided by log lambda. Now question is, well, where is the, I think I can erase this, we are almost through. What happens to the correlation length? I have scaled things by, I have scaled the momentum by a factor of b. So it is the momentum scaling went from p to q, which was b q equal to, so that's your p going to q, which is to put the to b over p, b times p. Remember, b greater than 1. All right, so q went to q in q space, you went from, in momentum space, you went from p to, so the q, so the q's increase by a factor, the p is rescaled by a factor greater than 1, and the length scale, what has happened to the length is, it is now the inverse over here. So the b which is greater than 1, it means that length scales now, that if I go from t to t prime, the t prime is further away from criticality. The free energy that we are talking about, f of t prime, rather, sorry, free energy, not the free energy now, the length. The length in the problem, psi t prime, is now going to become smaller than the correlation length at temperature T. And what is the scale? The scale is by B. So the correlation length when I'm further away from criticality at T prime is smaller because of this transformation over here, that scales, the momentum scales are increased by a factor, rather, I mean, the measure of the momenta increases by a factor of b, the measure of the length decreases by a factor of b, and therefore the unit is what is changing here. The unit is what is getting bigger, and therefore the measured length is becoming smaller. So it is xi t prime is xi, and you go on. So t prime is equal to some lambda times t, as we have said, which is what comes from the statement that we made, that m prime square is equal to b square times m square. So t goes like t prime is equal to some lambda t, and therefore this is xi of lambda t, which is equal to xi t over b. So xi t over here is equal to b xi to the power lambda t, and equal to several times n times, and it is b lambda n times t. And that is equal to 1. So xi of t is going to behave as, you set that equal to 1, and xi of t is going to behave as, so t n much greater than 1. So xi of t goes as b to the power n, and then this is of the order unity. So large a number of iterations, and you are going as b to the power n, and b to the power n, as we the n as we just found is equal to, so where are we? This is the n is what we had to look for. Here it is. So n is equal to minus log t over log lambda. So xi is proportional to b to the power n, which is proportional to b is like rather the n is like, I mean, it is this xi is like b to the power n, and b to the power n, which from here is the n from here is minus, so b to the power minus log t divided by log lambda. So that is what you see the n being. So the n over here is minus log t by log lambda. So xi is proportional to this, which means that it is equal to, so this is equal to 1 over t to the power log b by log lambda. So that's 1 over b to the power t to the power, right? So if I take a log, so this is b to the power log 1 over t log lambda, and therefore if I take a log b times log 1 over t log lambda, there should have been a minus sign, is that right? This is t b to the power n is b to the power log, so this is log 1 over t log lambda, and therefore it is 1 over t to the power log b over log lambda. So this is 1 over t to the power 1 over t to the power log b by log lambda, and that tallies. So if I take a log, it's log 1 over t by log lambda times log b. Take a log, it's so 1 over t, but the correlation length exponent, the correlation length is supposed to go like t to the power minus nu, and therefore the nu is equal to, so nu is equal to log b by log lambda. So here we are. So nu is equal to log b by log lambda, and there you find that this is this, and therefore this is equal to b. So here is the vital piece of result, that 2 minus alpha, and this has nothing to do with the Gaussian model. What we have gone through is just a question of changing scales and looking at what happens as I change the scale. So what the renormalization group transformation, which is essentially simply changing scales and changing scales repeatedly, that is telling you that 2 minus alpha is equal to d times nu. The specific heat exponent gets related to the correlation length exponent through the dimensionality of space. So 2 minus alpha is d times nu. So that all right. So that's done. That's a very important relation which we had not done before. We had done these alpha plus 2 beta plus gamma equal to 2 and similar a couple of other relations of this kind. But here is a relationship which brings in explicitly the dimensionality of space. We had done gamma equal to 2 minus eta times nu. These were purely thermodynamics which gave this thermodynamic relationships between physical variables which gave rise to these scaling laws over here. Here is a scaling law which is actually dependent on the spatial dimension, and you really need to go through this exercise in order to get a feel for how 2 minus alpha equal to d nu comes about. So here we are. So now back to where we were to finish off this Gaussian model that we were talking about. That what is this? I have the 2 minus alpha for went through that for a very specific reason, as you will very soon see. So, all right. So the question is, what is the relationship? What is this nu? Nu is log b by log lambda. And I have here the relationship which is m prime square is equal to m square times b square. This is t minus tc. So t minus tc is delta t. So delta t prime is equal to b square times delta t over here, which is t prime is equal to b square t. So this lambda, the t prime was equal to our lambda t. So the recursion, the relation that I have over here between m prime square and m square, now recalling what m is all about, that it is proportional to the difference from the critical point. It's proportional to delta t. So it is t prime, which is m prime square. M square is t. T prime is equal to b square t. Therefore, but t prime is lambda times t. That is the way we defined our lambda, and therefore the lambda is equal to b square. So Gaussian model. So Gaussian model, lambda is equal to b square. This is Gaussian. This is Gaussian model. This is general. T prime equal to lambda. T prime equal to lambda t. That just says that lambda is an eigenvalue for going from the set of variables which is t and other coupling constants to t prime and other coupling constants. T prime equal to lambda t is the relation between old and new t's, and this is Gaussian model specific, that t prime is this b squared t, and then the lambda is equal to b square, and 2 alpha, the nu which is log b over log lambda. So lambda is b square. So nu is equal to half. So Gaussian model nu is equal to half. So that is and gamma immediately works out to be 1, because there is no eta equal to 0 in Gaussian model. So gamma is equal to 2 times nu is equal to 1. And now it is a question of finding the specific heat exponent. So 2 minus alpha is equal to d over 2. So alpha is equal to 4 minus d by 2. So Gaussian model specific heat is alpha equal to 4 minus d by 2. I think that when I had done the Gaussian model explicitly by working out the partition function, that integral, we had calculated the specific heat exponent. If I had not, I can't be absolute. I certainly remember doing anyway. I mean, you can, if not, it is very important for you to check that Gaussian model explicit calculation. Explicit meaning evaluating the functional integral. Explicit calculation, which is evaluating the yields the relation over here, alpha equal to 4 minus d by 2. So this is we did not do an explicit calculation over here. We just calculated the transformation m prime square equal to m square b square, and from that we obtained the. So why, I mean, what should you, I mean, focus on? What one has to focus on, that in this process of getting things going and calculating exponents, I have not worked out a single integral. This is the very important issue, that we have done the Gaussian model before, but the Gaussian model, when we did at that time, was explicitly working out this functional integral. We actually worked out d phi e to the power minus integral ddx m square a phi square by 2 plus half grad phi square. We actually worked out this. This is the partition function, and we worked it out in order to get all the answers. So that integral had to be done. Here we have not done any integral at all. We have just essentially done some scale transformations, eliminating variables, which is the expression of scale transformation, and from that we have obtained, obviously we have used the scaling hypothesis, which is that this f or everything depends on T minus Tc, and the free energy has the specific form that, I mean, specific form meaning that things are or the only dependence that I'm interested in is the dependence on delta t, which is t minus tc over tc. So we have made a statement over here that things which we are calculating are going to be determined only by this scaling variable over here, this delta t, and the fact that there is a correlation, essentially a correlation length, which becomes very big, and things are being determined by the correlation length as the sort of unit which is the which sets the scale for the problem. So this correlation length has set the scale for the problem. We are not talking about the system size or things like that at all, which is why we focused completely on the intensive variables and not things which depend which scale with the system size. And we could carry out this calculation without taking recourse to any actual integration process. I mean, this is that is a functional integral process. I have done no functional integration in order to solve the Gaussian model. So, I mean, that is something which is the main feature why all this has been done at so slowly for a class and a half almost or more. That is simply to highlight that this process of using a renormalization group approach, where you remove certain degrees of freedom and then say that do appropriate rescalings to make your old new free energy look like the old. This process of doing things actually yields dividends. You can, without doing the functional integral, get at the answers. So this is the Gaussian model. I mean, please go through it very carefully and try to appreciate that the last time I did the Gaussian model, we had worked out integrals and we had done it at great length. Here is the Gaussian model, which I have again done with a lot of steps and time so that you can appreciate the difference between the two ways of doing things. This difference is very important when we go away from the Gaussian limit and we actually go to the Ginzburg-Landau free energy. When we notice that the free energy which one needs to use is a phi squared by 2 plus half grad phi squared plus lambda over 4 phi to the power 4. This is once again a scalar field theory. If I were to use n vector model, if phi square is phi 1 square plus up to phi n square, then the phi 4 would have to be phi I, phi j, phi j. So that's the n vector generalization, and the gradient would be del I phi j, del I phi j. But all that changes is the combinatorics without changing what the philosophy of things are. But so the real issue is, I mean, the challenging, because we could actually do the functional integral in the Gaussian case, without this term over here, we had the answer before. But what now I showed you that I can get that same. Now, the point is, if I knew only the Gaussian and I wanted to do this, I would get nowhere even in, so Gaussian plus perturbation theory goes nowhere. I mean, if you say that I have to calculate, for example, the susceptibility, the physical quantity that one calculates, for example, is the susceptibility, which is the integral of the average value of phi x1, phi x2, which is the phi k, phi minus k, and limit k going to 0. So if I want to calculate the thermodynamic susceptibility, for example, then the point would be that I would, if I wrote down, if I tried to do a perturbation theory, that is, use this, calculate this correlate. Sorry, it's the expectation value. If I calculate this, try to calculate this correlation function and try to take the, you wouldn't be getting the perturbation correction that you would get. The first order term would obviously be the Gaussian, which is k squared plus a. You can take the limit of k going to 0, and the answer is 1 over a, which is 1 over t minus tc, because this a over here is some a0 times t minus tc. So Gaussian, everything is fine. Try and do the next correction, and if I want to do the next using this as in a perturbative manner, so I simply treat this as a perturbation and do the next term. The next term plus functional integral by perturbation theory. This, so you pick up something where the integral blows up. So that is where the problem is. And that, therefore, the standard way of doing perturbation theory is not, will not work, as you can easily check for yourself. And therefore, I need a different approach. And that is the different approach that we have gone through till now. And what it said was that don't do it, don't calculate it as integrals, just sort of relate this problem to a problem which you see at a different length scale, and then compare the how these coefficients a and lambda change as you do thin out some degrees of freedom. So that is what the next step would have to be. I mean, we will So what is the story? All right. So I am, once again, the basic point is you have to calculate the partition function. And the partition function is d functional integral phi e to the power minus f. That is the partition function. Except that now your partition function is this, and let me write this down in momentum space. So it is equal to integral d phi p, these string of phi p's for every p, and then it is e to the power minus it is integral ddp over 2 pi to the power d a plus p squared by 2 phi p phi minus p minus lambda over 4 integral d3p1 d3p2 d3p3 2 pi to the power 3d, and then it is phi p1, phi p2, phi p3, phi minus p. So that's what the partition function looks like. This is a partition function which I know how to do, and what I said just now is that if I said that I know how to do this and all those with a string of phi's here, and therefore if I expand this, and that perturbation theory simply does not work. That is, if I assume that lambda is small, and so all right. So that will not work, and that is why we went through this a whole business of saying that phi p is phi p greater plus phi p less. So which is that you take this refers to all this refers to all p greater than some lambda over b, and this refers to p. So lambda greater than p, that's this part over here, and p less than lambda b, that's this. So our attitude was that take p, split p into these two ranges. And going from this to this, which means that what phi, in terms of the Fourier transform, phi p is equal to, this is going to be ddr phi r e to the power I p dot r. So that is the Fourier transform. So all the phi p greater relates to all the phi p's which have Fourier which correspond to p lying between this and this. And when you say phi p p less than this, then this Fourier transform is being done with all the p's less than lambda. So that's the split. All right. So now what? Now what we did was that we went and wrote this as phi p. I mean, over here life was simple because I could write phi p as phi minus p plus phi p greater, phi minus p greater. So this is the this happens simply because, I mean, if I had any if you, the terms which are going to look like this, you know, I mean the other which is, I mean, so two of these essentially. So terms which look like this are not going to survive they are linear terms over here, and linear terms are not going to survive in this quadrant. You are going to integrate all. When I'm doing an integration over the phi less, this is just a shift in the should have been, I mean, yeah, two of them actually. Anyway, so when I do the integration over the p less, for example, then minus p less, then this is a quadratic term which I'm looking at over here, this p less, and these are terms. So units like these, phi p, phi minus p, they are the only non-zero contributors to this functional integral. If I have phi p something here and phi p something else over here, that does not contribute to the functional integral, and therefore, I mean, we didn't have to worry about about the quadratic part. There is nothing to worry about. But things get problematic. Things become problematic as soon as I'm going to this term over here. I'm going to have terms which are phi greater. I mean, there are 4 terms of this kind. There are 4 terms of this kind, and therefore when you write this, it is going to be 4 terms which are phi greater. There are going to be 3 terms which are phi greater and 1 phi less. Then there are going to be 2 of each. Then the 1, 3. And then all lower. So as soon as I write this thing over here and put it in over here, I will be faced with these 4 kinds of terms. This term, which is all lower, I'm comfortable with. So that over here, I have this term over here is simply going to be phi greater, and plus phi less, phi less. So the p's which are big and the p's which are small. So that's this is greater than lambda over b, and these are smaller than lambda over b. So fine, I mean, and then it is the greater ones which you have to worry about. They are the ones you are going to remove. So phi less. Now, who else is going to stay? All 4 phi's, they are going to stay. Fine. All 4 phi's which are positive, which are greater, would have to be integrated along with these over here. And then there are these 3 and 1, they would average out on taking an expectation value, the 3 ones. And then there is this 2 and 2. So the 2 and 2 will survive, the 4s will survive, the others would go away. But survive and do what? That is, can I mean, I write this out over here. I mean, I substitute for this as this, easy. I substitute for this, and now you have not so easy because it looks like a mess. So what am I supposed to do? The only thing that I know how to work with is a perturbation theory. So come what may, the point is that I would have to perturb this, I would have to expand this exponential and do 1 minus lambda plus lambda square and so on. So, all right, so let's take that first step and write that and see where I'm going to go. Yes? এটা তিনটে গ্রেটার একটা লেস, হ্যাঁ, সো চারটে গ্রেটার, তিনটে গ্রেটার একটা লেস, দুটো গ্রেটার দুটো লেস, তিনটে এই একটা গ্রেটার তিনটে লেস, চারটে লেস, 4 রকমের টার্ম, এটা গুণ করলে কি? হ্যাঁ হ্যাঁ, এখন কেন 0 হবে? ইন্টিগ্রেট করলে 0 হবে। এখন তো জাস্ট গুণ করে লিখেছি না? Yes, you are right, যে ইন্টিগ্রেট করলে ওগুলোকে আমি ছেড়ে দেবো, শিওর, অ্যাবসলিউটলি, ইয়া। কিন্তু এখন তো ইন্টিগ্রেট করতে পারছি না, মানে ইন্টিগ্রেটটা, সো অল রাইট, ইয়া। নাও I have no bother. So what do I do? What I do is the following. All right. Just one step and what I do is I write e to the power minus ddp over 2 pi to the power d a plus p squared. This is 5p 5 minus p. This is all going from 0 to lambda over b. So this is entirely less. And then you write the lambda over 4, and then you have this phi less, e and then yeah. So right, the dd p1 dd p2 dd p3. No, there's nothing. All right, I mean, it is just grouped. That is something I will do the integration over all the phi's which have p greater in them. And what I'm saying is the only thing I know how to do is perturbation theory. So, all right, now over here, this is all integration over phi which is less. And so this is entirely over phi which is less. And then there will be d of phi which is greater. And less, integral over less means that it is only less terms over here. Integral over the greater means that there is e to the power minus lambda over b to lambda, and then there is a plus p squared by 2 5p 5 minus p, and then the other terms are all involving lambda over 4, and there are terms which are like 3 greater phi's, 1 less, or 1 greater and 3 less, or there are 2 greater, 2 less, and there is one which is all greater, right? So, all right. So this is the part of the integral that I have to carry out. This is all greater. So I don't touch these. I do only this. And how? There, what I will do, there is only one way I can do it, because Gaussian integrals are all that I know, and therefore I will have to expand. So how do I do this? I'll stop in a minute. I will write d phi p greater e to the power minus this lambda over b to lambda a plus p squared by 2 phi p greater phi minus p greater. And then I expand 1 minus this lambda over 4 and all the stuff that you have over here, phi greater, phi greater, phi greater, phi less, plus phi greater, phi less, phi less, phi less, 1 greater, 3 greater, 1 less, and then the part which is phi greater, phi greater, phi less, and then there are 4 phi graters. So this is, and then it is plus half lambda over 4 square, and then there will be 2 factors of this kind. So you start looking at things. If I have 3 graters, the answer is 0, because it's a Gaussian integration. It is like doing e to the power minus x squared times x cubed. Answer is 0. Here it is 1 greater, same argument, the answer is 0. Here it's no longer, this has 2 greater, 2 less, you have to handle them. Here you have 4 greater and you have to handle that. So, all right, that's but 4 greater, all right. And then there is this, once again over here, there will be mixed greater and mixed greater and less are all greater, right? So that's what you will be having. Now what? If I have all greater, I'm not worried, because all greater is a number. There is a difference between this term and this term. This term is going to give me back phi less, which will have to go over there. That is, the phi less that you pick up from here is going to change the coefficient here. But this term, which is phi greater phi, this is just a number and I'm not worried. Similarly, when you start looking at this too, there would be terms which have a mixture of phi greater and phi less, and others which are only phi greater. Only phi greater is of no importance. It is only the mixed even powers of phi greater and phi less. That is what you need to focus on. So this is the story that those have to be taken care of, and we'll pick it up from there, or rather from this point next time, and complete this part of the course. That what will happen is that these phi greater integrals are going to change this coefficient that we know already, that this was m square, a is M square is what is A over here. So M square changed. So A is going to change, that is, but it is the lambda itself, which lambda, the coupling constant, which is also going to change. And you would be having other higher powers generated, but higher powers you are not worried about, because we have seen that those are not relevant. All higher power terms flow to zero under renormalization group. As you change the scale and make the scale bigger and bigger, the higher powers than 4 go to zero. I'm not interested in those. So all that I'm interested in, there are terms which are up to 4 orders in phi greater. So that is what we will have to pick up: 4 orders in phi greater, 2 orders in phi greater. So what comes from here, that will be the non-trivial contribution, and that is what we will have to focus on. So go back, I mean, well, as we meet on Friday, think about this. All this is somewhat complicated, and look at it carefully. I mean, do have a look in your notes or in any lecture notes or books which you want. Have a look at it up to the point that we have gone so far. See what you read, or your that what is confusing, and we would clear that up and then start, because we are almost at the end of this business, and that should be a relief for you. Once you understand what's going on over here, the philosophy at least, and the calculations would be, we would not be going into any very involved calculation at all. It's the philosophy of what is being done is very important, because that you would need as a way of life if you are going to be a theorist. So that's very important. So that's the business. So we'll meet on Friday and finish this up, and next week we start with the dynamics part of the course, the approaching equilibrium in very good.